My name's Rich Corsi, and I'm honored to be the chairman of the Department of Civil, Architectural, and Environmental Engineering at UT. We have a great community. Our department is a great community. We have great students. We have great staff, some of whom are here today, great faculty, and great alumni. And I really do consider you part of our community. And I think the community is a continuum, and so what I've tried to do on this first slide is to reflect that. This is the class of 2019, so these were our entering freshmen this year, and 4 or 5 years from now, hopefully they'll be, many of them will be working in Dallas, and they'll be coming to alumni seminars like you are today. So that's our continuum, class of 2019, and all of you as our alumni. I want to thank CP&Y for offering their facilities. Not only offering their facilities, normally the department pays for the lunch at these events, and CP&Y offered to pay for lunch today. So they're providing both the facilities and lunch. So I want to thank CP&Y, and I especially want to thank Walter. Walter was a graduate, I think, a Master of Science in Environmental Health Engineering in 1970, I believe. So who here graduated before 1970? Ah, wow. So good chunk of the crowd. So thank you all for coming out. A young crowd. All right. So a lot's happening in the department. I'm going to go through a lot of slides really quickly just to kind of give you an update on really exciting things that are happening in the department before I introduce our speaker today. So the first is, for those of you that remember Concrete Canoe, is that ASCE's Concrete Canoe team just dominated the Mexico-Texas regionals and is going to nationals. They got first place or second place in almost every single category in the Concrete Canoe competition, first place overall. And the nationals are actually in Tyler, Texas this year. And so if you have some time, check out our website. We're going to have lots of information about the event, and maybe some of you can actually go and support our students in Tyler. David Maidment, who some of you know, was elected to the National Academy of Engineering. David is a leader, a visionary. He's literally transformed the water resources engineering field. David's not only somebody who's received a lot of awards in his field, they have awards named after him in his field. So he's very deserving. We're very proud of David. One of our graduates, Josh Aldred, Major Josh Aldred, I guess he's Major Dr. Josh Aldred now, was recently named Federal Engineer of the Year. He's just a wonderful person. He's done several tours in Iraq and Afghanistan. He's currently in South Korea. And to give you some perspective of what this means, every major branch of the government gets to name their Engineer of the Year. They pare that down to 10 engineers. They all go to Washington, D.C., and then one is named. And there are 100,000 engineers in the federal government. So a UT graduate was just named 1 in 100,000 of the federal government. And he's an incredibly wonderful person as well. Serves his country and also serves his profession. Very excitingly, we were recently listed as the number 2 in the U.S. News and World Report rankings for graduate programs in civil engineering, tied with the University of Illinois, just a smidge of a fraction of a smidge behind Berkeley for number 1. So we're really close to being number 1 for the first time, but in fact, we're number 2 for the first time. We've never been rated as highly as number 2 before, and so we're pretty excited about that. If you look at the tuitions here for us and our peers, you can see not only are we a great program, a highly rated program, a very well-respected program by our peers, we're also a really inexpensive program compared to our peers. So on a per-buck basis, we're doing really well. Environmental engineering moved from number 6 last year to number 4 this year. And again, you can see what an outstanding value our environmental engineering program gives our graduate students. By far the lowest tuition of any of our competitors. We had a BS program in environmental engineering that we've been working on for a couple of years. There's a huge demand for this program. We get a lot of calls from parents and high school kids about environmental engineering. That program has been approved every step of the ladder except for the Texas Higher Education Coordinating Board, which is sitting in it right now. So we've got our fingers crossed that it'll be approved very shortly, and we'll have a new degree program in environmental engineering starting in the fall of 2017. Several faculty promotions, all from assistant to associate professor, have happened in the last year. Steve Boyles in transportation engineering was promoted to associate professor. A real brilliant young researcher in transportation engineering. Fernanda Leite was in construction engineering and project management, was promoted to associate professor. If you've ever met Fernanda, if you've ever seen her speak, I mean, Fernanda will be a superstar, but also I think she's destined to be department chair someday, hopefully very soon. I'm kidding about that. And then Ing Ju in our Building Energy and Environments program also was promoted. And Ing is perhaps the top researcher in her field worldwide today at a very, very early age. Does great research on indoor air quality. We have 3 new faculty members. Casey Faust joined us this fall. She's in the construction engineering and project management area, and her research focuses on decaying infrastructure and construction management issues around decaying infrastructure. This is Casey here with Lynn Katz, and it looks like Alec in the background photobombing them. Salvador Salamone in our structural engineering area focuses on infrastructure health monitoring. Comes to us from SUNY Buffalo, a great researcher and wonderful teacher. The students love both Casey and Salvador. And then joining us in about a month or two is Zoltan Nagy from ETH Zurich, and he's in our building energy and environments area. We also have 2 searches underway that are almost concluded. I'm negotiating with 2 people. Young faculty really negotiate hard these days. But one in structural engineering and in dynamic behavior of reinforced concrete, and the other one in water resources engineering associated with failures of water distribution systems. We have some special events coming up. You're at one of them right now, so I don't have to dwell on that. There are 3 more alumni events at the dates that are shown here, one in Austin, one in Houston, and one in San Antonio. We record these, and you can go to our website, usually about a month after the last one, if you want to actually see the seminars, the presentations from the speakers at different events, and that's a place where you can do that. As I mentioned last year, David Fowler is retiring. We're going to have a symposium in honor of David and David's career on May 13th at the Pickle Research Campus in Austin. I hope some of you that know David are able to make it to that event, and if you'd like to know more about it, please see me after the presentation. And then in September, there will be a STEER event at the Ferguson Structural Engineering Laboratory, and Jim Yersa will be honored. His career, his accomplishments will be honored at that event. To do all the things we do means continuous renewal and renovation and that type of thing. I mentioned last year that we're trying to transform the first 4 floors of ECJ Hall, the basement, first, second, and third floor, to the undergraduate nerve center in our department. And I'll report this year that we've actually done a really good job of making that happen. So we're roughly about halfway there. I'm not going to go through all the details I did last year. The third floor is really taking shape with a very, very generous donation from Tom Taylor and his wife. We're naming our new architectural engineering design studio, which is 50% larger than the previous architectural engineering design studio. All new features, really fantastic space. Just completed it, and the students just moved into it about a month ago. We have a ribbon cutting ceremony at the end of this week. It's a wonderful facility, and it's named after Datum engineers. It's the Datum Architectural Engineering Design Studio. We've also built new classrooms on the third floor here. We've got the funding to build new classroom here, tutorial space here. We're about halfway to the funding we need to build a large multi-purpose room like this for having seminars and having project-based classes. We have a large area that's a student lounge, and we're trying to raise money for 2 more classrooms. So when all is said and done, that third floor of ECJ is going to be really, really, really crackerjack, and it'll be a great space for our undergraduate students. Some of you have heard about the Legacy Campaign. We're building the Legacy Campaign funds up. So this past year, we were able to fund 9 undergraduate students on research through the Legacy Campaign, and they get a huge thrill out of actually working on research. What we try to do with the Legacy Campaign for undergraduate students is develop their own research projects, not just have them wash test tubes for faculty in the laboratory, right, for graduate students. And then we've been able to support a couple of graduate students also each year through the Legacy Campaign. Many of you give to Friends of ALEC, our annual giving campaign. That helps us in a lot of ways. That's good discretionary money. We use it for students. We use it to support new faculty when they show up to go to conferences and that type of thing. So those are very, very good funds. So with that, and I should say, if anybody has any questions about any of these things, you can speak with John Halton, who... John, are you here, or did you step out? Anyway, John is here somewhere, and you can talk to him about it. Ah, here he comes. Right, so John, your name and phone number is at the bottom of this slide. All right. All right, so that leads to today's speaker. And I want to say a few things about Ken. Ken is a giant, I think it's safe to say, in the geotechnical engineering field.
Only in my mind.
Only in his mind, right? In many other people's minds, too. Ken was elected to the National Academy of Engineering, I think, in 1997. He has received a whole long list of professional awards from professional societies, from ASCE and others. He's received every major teaching award in our department. He's received additional research awards at the University of Texas. He was a founding board member of the Network for Earthquake Engineering Simulation. I've known Ken for 23 years now, and I would characterize Ken as somebody who's very, very devoted and cares deeply for his profession. He really cares about our department, and most of all, he's really, really dedicated and cares for our students. And so I think that's sort of the pinnacle of why we should be in academia, and Ken reflects all of the good things about what academics do. So I'll turn it over to Ken now. Welcome.
Well, thank you for not talking about the bad things.
No, there's no bad.
That's a big help. I have my own rooting section here today as well. My wife is down there in the corner, and our younger daughter is there because we came up to be with her and her family this weekend. They live in McKinney, so it was our pleasure to come up here and help with an Eagle Scout project. Okay. I was told I have 35 minutes to give an hour-and-a-half lecture, so I'm left some slides out. You should appreciate that. And I'm going to be walking around up here if you don't mind. So I want to talk about effectiveness of inhibiting liquefaction triggering by shallow ground improvement methods. You'll see why in a moment. And it's some field shaking trials that I feel good about because only we at the University of Texas could do this. But it's using one of our machines, T-Rex, and you'll see the problems that they have in Christchurch, and really it was a wonderful opportunity for us. Okay. So there's a paper, not a big deal. But let's just go through. So Julia Roberts is right here. She's a co-author. Sung Moon Wong is right there. Brady Cox is right here. Fang Yu Meng is over there. And Sjoerd van Balagoe is not there. He's with the New Zealand group. But we work with them. That's me. There is one of our technicians. And this guy, Cecil Hoffpower, just listens to T-Rex and can tell if it's working or not. He's been probably working with vibrosizes, prospecting for oil and things like that. We use these now in civil engineering. I suspect we're the only one in the world. But we have not 5 of these, but we have 5, but just different sizes. This is T-Rex. Another one, Liquidator, is going to go to the first greenfield site in the United States for new nuclear power plants being developed there, and so we'll be the first one on site to start prospecting into the ground and finding out information they need. But yeah, we are just really lucky to have this equipment, and I want to thank you for it. The taxpayers have purchased it. Compliments of the National Science Foundation. Okay. Just a little bit. I'll talk to you for a few moments about the 2010-2011 sequence that hit the New Zealand, the Christchurch Canterbury region in New Zealand, and there was severe liquefaction. Present potential ground improvement methods for residential and low-rise structures. Why? Because when you buy, and everyone's required to buy, earthquake insurance in New Zealand, it also guarantees the ground will be brought back to what it was before the earthquakes. So that allowed us to get to do some special work. Discuss how we created instrumentation to put into the ground, how we characterized the ground before we shook it, show you an example of the shaking, and then the overall results, a little bit on blasting that we didn't do but we participated in, and conclusions. So here we go. Next please. All right, so this is New Zealand, the North Island, the South Island, the Pacific Plate, the Australian Plate, and here's the Canterbury, Christchurch region. That's the folks in New Zealand probably don't have to worry much about sea level rise unless you're in an area like this, because the whole place is going up, with these plates connecting. And we were just very fortunate to be a part of this. 400,000, 4 million people, 6 million sheep or something like that. But this region was horribly struck. And it was unexpected in what you're going to see, not all of it, but what you're going to see. Okay, the 4 major earthquakes that caused most of the damage. These are precursors, but these are the major epicenters. But so you can see the epicenters. You can see how many earthquakes struck the area, mainly small ones. But here's the first one from 2010. You'll see damage. The second one caused the most destruction in the Christchurch area. That had an epicenter right here, but was closer to the surface. We'll look at the Central Business District, then you can see June and December of 2011. These aren't fake pictures. So here is, yep, that's a sand boil. We'll describe that in a minute when the sand starts coming out of the ground because of high water pressures. But there's a large sand boil, and the people got out of the car. But in the February 2011, 185 people died. 80% of the business district has been torn down. It was so damaged it had to be torn down. It's changed the way they do business. They work from home a lot now, I can tell you. It's really changed it. The total economic loss keeps changing, but $40 billion, but it was bimodal. A lot of it, 20 billion was in high rise, and then the other 20 billion was in this low rise in residential structures. The insurers knew this one was coming, let's say, but they didn't know the residential structures. And so it was a real surprise, unhappiness, that caused it. You see 20% of their gross domestic product, 40,000, homes affected, 20,000 severely affected, and 10,000 homes. Now this is in 400,000 people. 10,000 homes had to be abandoned and torn down. Okay, just to put a building in there for you, that's the only building you're going to see. But this just shows you what happened in the Central Business District. 65 people lost their lives in this building. Now, do not think the New Zealand engineers are not good earthquake engineers. They're very good earthquake engineers. And this was just unforeseen. It was more than ever expected. Now, liquefaction for us, let me just review for you, and this is a new slide, by the way, just so that I could try to say, it's a phenomenon when a water-saturated soil, typically fine sand, gets loaded, and it could be dynamically or statically, gets shaken, the water pressure builds up, and it loses all strength. Okay, so here would be the loose saturated sand before the earthquake, and the grains are touching. But then when the shaking comes along, it isn't exactly like that picture, but when the shaking comes along, then the grain between all the skeleton, all the other grains will try to push into where the water is. When they push on the water pressure goes up. When the water pressure goes up, now the strength that was there because of friction, grain on grain, is reduced and really goes to nothing when the water pressure equals the vertical effective stress. So it goes to zero, and at that point, you just have a heavy fluid. And at that point then, the water pressure to the sides are the same. It's not going to go down. The only place it can go is up. And so it's going up, and then you see sand boils and things like that at the surface. And it's that loss in strength that causes tremendous problems. Now, I'm going to be talking about level ground where you usually have the least problems. Sloping ground is really bad because things start to move. Okay, but I'll be talking about level ground, and here's a sand boil. Okay, these are huge. There's a house. This is a subdivision. You know, there are houses, there might be 400, 500 houses in a subdivision. They're gone. They're gone. They've all been torn down. But that would be just one example. I should mention Mishko Chubernovsky, a very good friend, a professor from Canterbury, a very good friend of ours. Next. Okay, some examples. And Mishko has put all this together. So here's September 2010. This is a field hockey ground. It's over here in February as well. That's a sand boil. So the water pressure is built up during the earthquake shaking and just blowing this sand out of the ground, very fine sand. Just for the record, there's a car. They're huge. This is the same location in February. It happened again. It got much worse. What happens to you if you have a layer on the top that's impermeable relative to the permeability, how fast the water flows through the sand? It's much slower. So when that happens, the water pressure lifts that layer up, but it only goes through in certain areas, so the sand can sediment out beneath that layer and be looser after the earthquake than before the earthquake. So you would typically think that this densifies, and if you remember your soil mechanics class, you had a liquefaction tank and they turned the water on and it came up through it and the top raised up and then they whacked on the side and everything densified, right? That was just an example of what could happen. But in many earthquakes, that's not what does happen. Yes, part will densify, maybe down deeper, but you can end up with loose soil right near the top of that deposit that makes it even worse. We have gone back to Imperial Valley of California to deposits that have liquefied over the last 40 years 5 times. Okay, so, oh no, don't think that it's going to disappear after you go through a couple of these. Next. This, to me, I grew up in Michigan, and by the way, I did want to talk with Rich. Rich, I was only given $500 to move to Austin for my faculty hire. And I even had to rent a truck to move us. We used rider rental, didn't we, dear? See, I mean, you know, I want to renegotiate this. Okay. I needed that on film, just in case, you know. Okay. So here is, that's not dirty, that would be dirty coming from Michigan. That would be dirty snow, huh? No, that's sand ejecta. 500,000 tons of sand ejecta had to be moved out. So the joint settled. I mean, now it was just barely above sea level. Some places have moved down 1 meter. This area, that's the water and sand ejecta that came out of the ground. All of those homes have been demolished. They're all gone. So Russell Green, maybe a couple people here, a good friend of ours at Virginia Tech, who's really upset with us right now because we've stolen a lot of the top graduate students away this particular year, getting them in. Oh, erase that part of the film. No, he's a great guy, but no, we've been very lucky recruiting outstanding young graduate students, just like Rich Corsi indicated. Here, he put this together. It's in Quigley's backyard, so this is a professor that took these pictures, and I just wanted you to see the walkway, and you know, you can drive on it and so forth. I want you to see this walkway. There's a shed back here. And that's a little sand boil. I didn't even mention April to you, huh? That wasn't one of the big earthquakes. But this just gets us started. Okay, so here we go. This is the backyard, his backyard. There's a shed I spoke about. This is the September 2010. You can see nothing. Sand is everywhere. So it's all come up through the ground. Well, it's going to be good the next time. Let's hit to the next time. Here's February. It's worse. Now, this was all cleaned up between September and February. It's not like this is on top of itself. Okay, so here's February. Next. Here we are. That's that one where it just started, just to show you where we were. Here we go in June, part 1. Now you can see the sand boils here. I think you see some fruit on the ground. I'm not sure why, but I'll attribute it to the earthquake. See it a little better here. That's the second part of June. I mean, this just kept going on and on. And so it probably was one of the most interesting research opportunities we've ever had. So our National Science Foundation we got several grants. Other people got even more, but we got grants to go down there. Brady Cox, young associate professor now that we have hired, and I went down there. Ellen Rathje went down there. We've had a lot of people at work down there because of the interest in this and what can be learned, and we have learned a lot. Okay, this would be just a typical house. Now, like you can guess, they didn't have to investigate by the code deep enough to identify this. You could take a person knowledgeable in liquefaction in an aerial photograph and you can say, whoa, this is going to be trouble in this general area of town. But so the houses were built just slab on grade, very little reinforcement, and you can see cracking and all that. So they just didn't make it through earthquakes. And they were so damaged they couldn't be easily repaired or economically repaired. So what is the path forward? The critical problem facing them is rebuilding resilient systems. Okay, and that's what we very much tried to help them do. The land remains at risk. Just like I said, it can liquefy more times, no problem. They need to develop effective engineering solutions for these thousands of structures that can be repaired, and for new structures that they're going to build so that they'll be resilient. The solution has to be cost effective for them. Why? Because they're a small country. I mean, they say this to you. They're a small country. They can't have some proprietary technique that might do a great job be developed and sold down there because they can't afford it. So they want to try to develop their own solutions that their people can apply, and they can have some competitive contractor participation. And they need to be verifiable for insurance purposes. So we were also helping with that aspect of trying to develop verifying procedures that could be used. Okay, the path forward. Professor Ishihara is a very famous name to those of us in earthquake engineering. And he has gone through lots of earthquakes in Japan, made lots of measurements afterwards, and has determined that basically if you have a residential structure on something that looks like it's an effective, about a 3-meter thick crust, okay, that the structure will be damaged a bit, but it won't be torn apart like you saw here, and it can be economically repaired. So that was the whole idea, that this 3-meter thick crust need to be developed, and it would inhibit, it can't stop liquefaction triggering, but it would inhibit around this. If this were the footprint of the house, okay, we can have some liquefaction over there, over on this side, but the house on this sort of little boat will make it through and maybe only be a little cockeyed, and we can re-level it and so forth. We'll make the slab probably a waffle slab so you can jack it back up. By the way, I gave this same talk, a little longer version, a little more technical depth, but in Tokyo they weren't too interested. Why? Because they already build so that they have a waffle structure and they re-level their homes, and they just do this regularly now, huh? So I didn't get any earthquake research in Japan that I know of right now. But we're following what they're doing. We have field shaking trials with T-Rex, and I maybe didn't, that big machine that we were standing in front of is called T-Rex. T-Rex is known around the world, just for the record. So is Liquidator, so is Raptor, so is Rattler, so is Thumper. We have quite a few machines. Nobody else, no university in the world can do this. No, other than us. Okay. And we brag a little bit, too, to try to get raises out of the chairman. Okay, we are trying to come up with acceptable ground improvement methods and field verification procedures, not just one. All right, so here's the business district. This is the Avon River, and if you're talking with someone from Christchurch, it's not much of a river. But, there's the Avon River and coming out into the ocean. And this red zone is where most of the homes have had to be torn down. And Brady went down there early, Brady Cox, and we investigated several sites for their characteristics, particularly their stiffness. Then 3 different sites were chosen that had slightly different geotechnical characteristics, so it was important to us. But I'll just show you information from Site 6. Now, here's Site 6, and it's just a Google aerial shot of it. But here's Site 6. Shortly after, as best I can tell, the 2011 earthquake. Why do I say that? Because see how the roads are sort of gray? That's all sand ejecta from the earthquake. Those are all from sand boils. And don't worry about this. Those are going to be test panels where we're going to test. I'll show you another figure that will better identify this. But in the testing techniques, they would also let the contractors practice. And they'd even tell the contractors how well they had done the work in the practicing. And so the practicing was done over here. I'm standing here taking this picture. That's my rental car. See the houses? See what it is like today? When I say they're gone, thousands, 10,000 of homes. It's just like his pasture. This was the high rent district in the city. Now, they'll probably try, developers, we know developers, they'll probably try to figure out a way to get around this in the future. But what the key here is, well, how do you then develop this land so that you can build on it with some confidence? And we're trying to help them with that. Okay, here are the various techniques that we looked at. We had, the New Zealanders chose this. We had nothing to do with this. Okay, so here, rapid impact compaction. So here's a plate about 1.5 meters in diameter, and they're just beating on it. And they'll come and they'll do it in a certain fashion to densify the area. And so they're trying, again, to make this material denser near the surface to develop that 3-meter thick crust that we're talking about. Okay? And it would work, by the way. But they're worried that it'll hurt other things. But that will work. Next. Another one was rammed aggregate piers. These aren't stone columns, but if you're used to it, they can. The stone columns can also be used in something like this. And you've got the steel pipe that you're inserting down into the ground, and then you're ramming this gravel that's maybe inch to inch and a half in diameter, clean gravel, into the material, and you're pulling it out after you think you put a certain amount in. You know how much you put in. After you put a certain amount in, you'll lift up, put some more in. So you're trying to build this column. The column not only stiffens the general soil, but it densifies the soil because it builds up horizontal stresses, it vibrates and so forth. It does quite a good job. Now, you're going to say, a geotechnical out there right now would say, how do you know it looks like that? Every single place we tested, and we tested more than 50 different places, it might be 47, but it's a number like that, they trenched. Now, they trenched, and the water table is a half a meter down. It was a lot of money just to trench, but it was to check everything that we had done to see if it looks like it fits. We told them what it was with our non-destructive testing, but then they tried to check to see if it really was that. Here's low mobility grout, and low mobility grout is the only technique that was, I use the word was, in the earthquake code that was acceptable. After Professor Stokey was there, without even presenting any data while it was being collected in the field, it was like, oh my goodness, this is... And I have to, I'm now amongst relatives, watch what I say. Sometimes I don't use such nice words, but I've learned from the New Zealander, it was rubbish. Rubbish. Think of rubbish. I mean, it's the bad stuff, huh? Well, this stuff is no longer in their code. We have gotten calls from around the world. We are not popular in many places. Fortunately, I also have a mafia, so it's not so bad. Okay, now, I had never seen this before. The New Zealanders were very innovative, and they did directional drilling, then come back, so they directionally drill under the house. Then they put a different mixing tool on there, and they would come backwards, and they would mix fine cement with the sand in the top and build a single row or a double row of beams on top of the house, underneath the house, excuse me. And it turns out they can do that. And I'll show you in just a moment. But here is the site I said I'd show you, again, where our panels were. So we call them test panels of the different improvement methods. So here's a natural soil test panel. Obviously, there weren't any homes there at the time. They were demolished already. Here's a natural soil. That's the rammed aggregate piers where they're pounding the gravel into the ground. Here is the rapid impact compaction where they're just densifying the material. There's the low mobility grout that I mentioned. This is a double row of beams. That's a single row of beams. And then another natural soil panel. And we would shake when T-Rex, that's basically the base plate of T-Rex there for the shaking. We would build an array. That's a shaking direction. It doesn't matter. The blue square is the sacred ground. No one else is supposed to be doing anything in that ground but us until after we're done. Okay, next. So to do this now, it'd be like, okay, I have a nice little lab setup. I can put a membrane around it. I can load maybe back and forth on the top, watch how things move, see the material. Well, that's what we're trying to do, but we're doing it in situ, in place. And to do that, we need to put sensors in the ground. To get sensors in the ground, you call Stokey. Yeah, you don't call anybody else. Nobody builds them. We do. So we have to build these sensors. In fact, these are motion sensors. These are pore water pressure sensors. We don't need to worry more than that. So we can see how different parts, and it'd be going like this, how different parts of the ground are going. So you're shearing, and you want to see how the pore water pressure builds up. That's what the earthquake does. By the way, if you want to buy any of those, let us know. $2,000 a sensor. It's not cheap. And you saw 100 there. No, we built over 300 for just Christchurch. Okay, so here's T-Rex. On the back of it, we've added a ram, and we're pushing those sensors in the ground. They're keyed and all this. And then we can pull the rods back. We can put bentonite down there, and we can, once again, put a sensor at a known location. Water won't come flying out. It worked very well. I also told you, how did they know? They trenched. To trench, you had to de-water. They trenched afterwards to check on everything that was done. Next. So here's Sung Moon. He's digging a trench. Here's Professor Stokey with the camera. Okay, Sun Moon, smile. You know, he's a wonderful fellow. Here we're putting down a gravel pad. There's T-Rex. T-Rex had to sit on top of it overnight. There are the cables coming out. That's Julia Roberts. You're thinking of this one. This is Julia Roberts. Right there. And Sung Moon. And there are computers everywhere. It's very intensive. Now we tell T-Rex what to do. So we run with the computer. We run the machine. Very different than in general and very different shaking. Okay. We don't need to talk a lot about this, but here's a base plate of T-Rex. It's shaking. It goes through certain shakes. Here's the instrumentation down there. Let's not get too carried away, but we've got the instrumentation down there. We can measure motions. We can measure pore water pressures. You'll see 5 pore pressure transducers, 4 sensors. We're going to take that over there. It's going to look like a finite element. We'll move this over here as well. That'll look like a finite element. They're all within the base plate, so you're in the zone of major loading. And in fact, when we put the load of T-Rex on there, it's pretty much a uniform pressure over the depth of our array. And this goes down to about 3 meters, by the way. Aha, I see something's missing. It wasn't missing on what I reviewed. Next. Okay, so now we have to characterize the site. We won't get into this too much, but we push rods down, we pass stress waves, we pass compression waves, we're talking with compression wave, we pass shear waves. That's what the earthquake does. It doesn't matter if you're shearing like this or you're shearing like this right now. It's all going to give you pretty much the same stiffness within 5 or 6%. It's not a big deal for shear wave velocity. But we're going to characterize this zone. And I'll just tell you, we did some stuff they never expected. And I'll tell you, we could tell when the soil became saturated. If it's an unsaturated soil, it might not misbehave during the earthquake. If you don't know it's unsaturated when you're testing it, you've screwed up because you're going to think, whoa, This is working. And it's not working, it's just because it's unsaturated. So we took care of that. And that's probably one of the things that surprises groups like this when I speak around the world, because everybody thinks it's saturated starting at the water table, and that's not true at all. But if you deal with soil dynamics, you run into that very quickly. So here's T-Rex. We're pushing this middle sensor that's sensing motion. We have some portable rigs. We're tapping on it here. We don't. They rented them. We're tapping. We're passing waves through the improvement. We're passing between the improvement areas, so we can very well evaluate the improvement. We're going over distances like this length. So it's a small scale testing that we've done. Works beautifully. That's going to be the verification technique. Let me tell you, people don't like that, but it's gotten through in the code. Okay, so let's say this was the improvement, that gray zone. We would start at 0.4 meters, and every 0.2 meters we would go across and run these tests. So here is a real profile at site 1, 1A and 1B, because let's say that's 1A, 1B. But now it's a natural soil, so that's the same as this. There's no improvement there. And that's two different natural soil sites that I showed you, and that is, the black line is a median. We're going to use that to compare with all the other comparisons we're making, that black line. All right, so, because this gets complicated. So here's an improvement, here's an improvement. Now when it's a wrap, that's where they are pounding the gravel in. Okay, it'd be in the gravel column here and here. And now we're going in between them. Where it was the plate and just the wrap hitting on the top, that would be the location of the plate, location of the plate. So here's the natural soil, and here are the rick and the wrap. Now this is shear wave velocity. I'm sorry, just bear with me. That's a really important thing. I've been doing that since 1969, so it better be important, or I've been wasting a whole lot of time. This shows improvement, believe it or not. But going across the improvement is really important to see how well that changed that local area and localized area. And you see, yes, it did it for the rick, and oh, it did it a lot more, because now you're going through that gravel column that's very dense and under fairly high pressures. So, yep, those worked well. That's the bottom of where they went, and you can see things were improved beyond the bottom of that improvement. Next, or what they were gauging it. Here's what I indicated about the low mobility grout. It was in the code. While Sung Moon and I were collecting the first data, we were looking at it. While it was being collected, we started to get down here as like, holy mackerel, something's wrong. It's so slow. So the wave takes a long time to propagate just this distance. That's slower than anything out there. That hydrofracked the soil. They didn't do it correctly. I didn't say it doesn't work. I'm just saying the way they did it, they didn't do it correctly. I've learned to say that, by the way. It took about 2 times before I got the message from contractors from around the world. So I'm trying to say it very well now. And I believe what I'm saying. But they did very poorly. Now, notice there are 2 sets here. That's because as soon as I saw that happening out there, because, by the way, you just don't send graduate students out in the field to do this, huh? So the professor has to go out there with them. Brady Cox was there. There were several professors. That's the way they learn, and that's the way we learn, but we pretend like we're telling them all this stuff, huh? You know, no, I mean, they'll ask great questions. Oh, why didn't I think of that? And it's just really nice to be with good students. And so we immediately knew there was a problem. And as I say, this was the only thing in the code that you could use, and now it's out of the code. And here is going across it, and that's the one thing that we all know as faculty. I can tell you, when you put grout in the ground and you're under high pressure, you have no idea where it's going, huh? To be honest, you know, you draw this nice bulb, and that's not what's happening. But we had to do a bunch of other stuff. I'll just leave it that way to prove to the contractor that they were not doing things correctly, to make some suggestions, and we've left it. But this is not going to be used. Next. So this is just to give you an idea. So here's T-Rex. That's full scale. This isn't drawn quite correctly, but let's say those are improvements. There's an instrumented zone right beneath the base plate, huh? But that's almost to scale that way. Okay. And here would be the base plate. This would be like wrap, so the rammed aggregate piers. And we'd be shaking. Okay? That's where we would have done the cross-hole test right nearby to evaluate it. Okay? Now, what you do, just like in the lab, you can do stage testing. And so we do stage testing in the field. So let's just say this is 1 p.m. one day. We're going home to go to bed. This is the next day we're shaking, we're demobbing, and then we're leaving. So this is like a 24-hour period. So right in here, we would have done this shaking part. So we were doing about one site a day when we really were working hard. And I mean, you're working 12, 14 hours a day. But we would install these sensors in the ground, create this array, know where it is, then put T-Rex on top of it to let the material consolidate. Not the sand down below the first meter, meter and a half. Not that, but the stuff in the first meter, because that's silty and even got a little clay in it, and you want to squeeze the water out of that as much as you can to get it as strong as you can. Okay, and then we'd come back the next day and we'd shake. And so here's T-Rex. Now this is very well coated. Yellow, yellow, shaking, shaking. Okay, so there we go. So here we go, and that's not, I don't know, one of the Simpsons or whatever with the hairdo, but you know, that's supposed to be this, the cycle. So this is, we're shaking at 10 hertz for 10 seconds. We're putting 100 cycles of loading on it. This is a real law. Bzzz, you know, nothing happens. Good. You got to know when nothing happens. Then bzzz, we got a little more force, huh? And nothing has still happened. Then we start just building a little bit of pore water pressure, so you can see now we have to let it equilibrate for just a bit. We shake some more, we got to let it equilibrate, and then we give it everything we got. Now, we have a problem because T-Rex is too good. That is, it's too strong, so it's not as flexible as we'd like, and it can't follow after a while because the ground's starting to move too much. So we never liquefied anything. I want someday to be in the newspaper with liquidator sunk up to its, you know, just so we barely see it. No one got hurt. We'll pull it out. It's no problem. It'd be wonderful to liquefy something. We're going to try to do that in Portland, Oregon. Oh, this is a wonderful, no, you can hit it.
Sorry, just
I can hear it, no problem. So, oh yeah, we were hot stuff in New Zealand. Not here in Texas, but we were hot stuff in New Zealand. So that's our instrumentation van. Here's T-Rex setting up. You can't do it this fast. This was just for the movies. And we'll set down. We'll put a load on it, and I will start shake. Watch right here. Okay? See that water pop out of the ground? That's not liquefaction, by the way. I guess it is, but it's so localized. It's just the near-surface stuff. It's not the stuff that did anything bad. But that's what you see. I mean, you're shaking it like that. And this cost a lot. They spent more than $1 million on us. You spent $200,000 on us. So we were famous there for a while in going in the country. Who are you? I'm the dad of T-Rex. Oh, come on in. You know, yeah, I was treated better there. Not better than at home, of course, dear. Yeah, but I was treated very well there. So here's our soil deposit. Here's a water table at 1/2 meter. And this is really, to a person like me, this is gold, huh? So here are pore pressure transducers. That's all you're looking at. And this is 100 cycles of shaking. And you see, the thing that matters to us is not the peak to peak there, it's how it's building up, building up, building up. And that just says the pore pressure ratio, pore pressure ratio is the excess, that's that average, divided by the initial vertical effective stress. We don't need to worry about it, but let's just say when that equals 0, you're in trouble. Huh? Or 1, sorry. When that equals 1, you're in trouble. And what you see at small shakes, this is not saturated, but we won't get into it. At small shakes, nothing's happened. That's good. And we're going to follow this guy. We're going to follow the 2.1 in a minute. Next. Here you see the things build up. You see different responses. I can't explain them, This is real stuff. This is real. This isn't a laboratory test. This is out in the soil. That even called dilated. In other words, it generated negative pore water pressure. We wish everything did that. We wouldn't. No, we don't. We wouldn't have been there, but we do. So those people would be in good shape. But let's look at this one. That's a 32% pore pressure ratio. We're very proud of that because this will tell us what's going to happen. So here we go. This is the pore pressure ratio now, just expanding to 2.1 meters. And here it's going up nicely, but then it starts to level off. That's because we become displacement controlled. That's great data. Here is the shear strain. That's what we can calculate now, knowing how one part is moving relative to the other part to strain in that zone where that pore pressure transducer is. So this is great data. Next. So here we are at that one site. That's where the pore pressure transducer is. This is the stuff that's the bad actor during the earthquake. Loading stages 1, 2, 3, 4, 5. 1. This is excess pore water pressure. That's the bad stuff for us. 0. Tiny strains. Wonderful. Okay. Another one. Nothing happened. So that was the first 2 shakes. That's just what we want. Now, we generated some pore water pressure. Maybe you don't think so, but we did. And so we see just a little bit. This is a big deal to us, and I could talk about this for another hour and a half, but we won't. I have all kinds of slides to talk about it with. But this, we have another threshold now when pore pressure begins to be generated, and we're working very hard on that. That's very important to geotechnical earthquake engineers. Professor Dobry, a good friend of mine, has worked on it a lot. And now we're starting to see the next to the last shake and the last shake. That was the one that had 32% pore pressure ratio. I can tell you what's going to happen now. Well, maybe everybody doesn't believe that, but we can say, no. This is going to liquefy during a major earthquake. If we could have followed it, we would have been in trouble. The New Zealand engineers were overjoyed with this. This just shows you at that one site that did horribly during the earthquake, Did horribly during the earthquake. This is the deepest transducer. That's the next deepest. That's the one we were looking at, 2.1. This one's not going to cause any problem. That's got all the other characteristics, but that shows you the variability you're going to find. And remember I said 1 dilated, that means the pore water pressure went down. When it went to shake, the particles came apart in the pore water pressure. They tend to expand, and that pore water pressure went down. You will never get that out of a laboratory experiment. You're only going to find that in the field. Next. This is the summary of all of our data, at Site 6 at least. So these are bad actors. I'm not showing you the stuff that didn't act poorly, just the stuff that did act poorly. So here are the bad actors, and there's a band that you would predict would liquefy during an earthquake. And the triggering of liquefaction, not that it matters to you, is a moderate strain. It's not a strain at failure or anything like that. It's a moderate strain phenomenon. And I don't want to say more than that, but many... Hey, who did that?
Sorry.
Who did? Did you do that?
Yes.
Oh my goodness. This, when I've shown this to various groups, they say, well, we really prefer this. And that's coming out of a lot of labs. That. Remember that word from New Zealand? Rubbish. This is rubbish. This is real. And, you know, it was very nice of Professor Corsi, who I just think the world of. When did we get evaluated? Have we been evaluated yet?
You were on the committee that did the
Oh, okay. Well, I rated myself highly. It was okay. Okay. You don't get to rate yourself. Sorry, I'm going off on a tangent and having too much fun, and I even forgot what I was going to say. This sort of stuff, though, is so important for the future that we couldn't be happier with it. Okay. So, and he said nice things about me, but that means 2 things at least, those nice things. you're lucky. You have friends. Oh yeah. If you're not lucky and you perturb everybody, you probably don't win any awards, or many. Okay, what's luck? So, Julia Roberts and I were down early on when Brady had this going for deep seismic profiling, and we wanted to get a project with NSF. And we've done this before, but we didn't have the data. And so Julia and I did a site, and there's the data from the site. It's the best site we did. It's the best site we did. So, we look good in our proposal. If we had this data, we wouldn't have looked so good, huh? So we were lucky, but it worked out for them. Next. I'm almost done. So here's blasting in addition to all the shaking. So we've shaken all kinds of stuff. We ended up putting all these sandbags. Those are sandbags. We helped put all those there. But they were also looking at some mats. A gravel mat and a soil cement mat, and that's a natural soil panel. What are all these hunks, the big blocks of concrete on there? That's to represent the house. So that's the equivalent weight of a house, okay? Next. So, they blasted. When you blast, you can liquefy anything. Oh yeah, honest. I mean, as long as it's nearly saturated or saturated. Well, I mean, this is sand boils and sand eject, everything is bad. So 15, can we go back? Go back one? Okay, there's 15. Forward. There's 15, that block. And you can just see all the bad stuff around there. Next. What happened is, that was next to the soil cement mat, or back behind it. But they did find that if they could build a continuous mat that was something like 1.2 meters thick, this was just their example, but this is the thickness that matters, that was soil cement that they could make under the house, so then you'd build your house on top of that. So that's for building new structures. It would work well. So our verification techniques dealt with seismic waves. And just like we were doing cross-hole tests, we'd call them going across the improvement. For this one, we use surface waves. So we can tap on this surface and we can run waves along it and tell you how good that is. And the first one I tested when I went down there after they started putting them in production was wonderful. The second one was garbage. Sorry, rubbish. Because the contractor, these were road, sub-base, improving the sub-base and so forth. These were road contractors. And the first one, there were no seams in it. The second one, there were seams and cracks, and the guy did a rubbish job. And it didn't work. The point being, after all of that, verification is very important, and so we developed some verification techniques for them. Now, don't worry, this is so we can get out of here quickly. These are real technical. You don't have to worry about them. As evaluated by T-Rex testing, shallow improvement methods that inhibited liquefaction triggering the most, RIC, RAP, double row of beams. What's the problem with double row of beams? They don't have a verification procedure, so they're not getting in the code now. They have to come up with some verification procedure for these. That's not easy. Did not inhibit liquefaction triggering, low mobility grout, single row of beams. Single row beams, they can put them in so well it looks like they didn't do anything good to the soil. Next. And there's more. But the recommended solutions from all the different sites were the ground improvement methods are RAP, gravel columns, and soil cement mat. They should be verified by small-scale cross-hole seismic testing. That's what we do. It could also be SASW testing, don't worry, another type of testing. However, if the cone penetrometer will show sufficient change between, like with the RAP and the gravel columns, between them, in an engineer's judgment, then that's acceptable too. That was a compromise, but no problem. And sometimes it does show it, sometimes it doesn't. Professor Stokey, Professor Cox, very distinguished people. This is Liam Witherspoon, who's a young professor from Auckland who we're training to do all this. And so this has worked out really well. And that's another graduate student. That's one of Brady's. So this is on another activity, and we got to lots of parks. It was legitimate for 4 men to sit on that, so don't think we broke anything. Okay, we have a good time. Next. I want to thank you guys for coming out. It is really nice. I hope there was something of interest for you. CPNY and Walter Ching, thank you so much for your hospitality, and thank you for your tax dollars through the National Science Foundation. This is Julia Roberts on a Graduate Research Fellowship. It's great. The New Zealand Earthquake Commission, as I told you, spent at least about $1 million on us. In the end, this turned out to be about a $7 million project, and you only saw a small fraction of it. But I mean, it was extremely important. And then we have good friends at Canterbury, good friends at the University of Auckland, and we thank our staff, which we couldn't do it without. I think that's it.
Questions for Ken?
What happened to the water and wastewater infrastructure when all this?
Oh, it was demolished. It took a real beating. The person who headed that up, his name is Tom O'Rourke. He's at Cornell University, and they have been putting in, you know, the not PVC, what is it? The plastic pipe with wall thickness like this. Everything. You know, so I don't know if you have a feel, but right, even at Site 6, I'm going to divert a little bit from what the answer there, but even at Site 6, I showed you where I was taking a picture, and behind me was a bridge. So what happened at the bridge? The bridge didn't move. It had foundations going down to good stuff. So a bump at the end of the bridge was this high. You ran into the bridge if you were going to try to drive over. So the point that I'm trying to make, though, is the infrastructure, all this infrastructure took years to repair. Years. And the last time we were down there was August of last year. They were still lots of stuff being repaired. It's just a huge expense. Sir?
You may have said this, but how many people were displaced permanently by all of that?
Wow, that's I'm thinking. Oh no, sorry. I was calculating 50,000 to start out with, and I was going up from there because that was the 10,000 homes to start with. You know, and they are the nicest people. I'll give you a good example. Many restaurants have been demolished, so I've eaten at McDonald's more in the last 3 years than I've ever done in my whole life, huh? But you go to McDonald's and you're waiting in line, no one cuts in front of you. Nobody even makes a move. Are you there? Yeah, okay, they get behind you. They are the nicest people. Okay, now why did I say all that? Because we're there with T-Rex the first time. We're making noise and everything, and they're saying, can you come over for tea? Because when 500 homes would be demolished, this just happens. There would be 10 that weren't hurt in the subdivision, huh? It was just like, it's a miracle. I mean, how come everybody didn't get, no. And so they would hear us, they would come over, they would want to share with us, they'd tell you about their experiences going through the earthquakes and stuff. They're just the nicest people. But what happens is just like here, huh? You demolish 10,000 homes. They have to move way far outside. And the home is 20% more. It's not cheaper. So the government made them leave the home. The government made them. They have to, huh? They condemned them. The government made them leave the home. Rightfully so. They should have. But then they just, and I didn't see anybody that was 25 in these homes. These people were getting very close to retirement if they weren't retired. So, they were in a great area. They could walk to the store, walk, and to the, so it really, really was a hardship on the people. You just can't imagine, and they're just the nicest people.
Ken, how did you secure this work? Did you compete with other universities for this work, or did T-Rex just give you the ticket into this thing?
Compete? No, we've been very, very lucky. No, nobody else could do it. No, there's no one in the world that can do it.
Now Napier is,
By the way, there are very few people in the world that want to do it either, so, just for the record. So don't think everyone's beating down the door to do this.
Napier is north of Christ Church on the coast.
Okay? Mm-hmm.
I forget how far, but they had a significant earthquake in.
Just recently.
They had
Oh.
one in 1908 or sometime,
Oh.
and it's totally, the whole town sank below the.
Is that right, below sea level? Sorry. Yeah, no, I haven't been there. They just had another one, maybe 2 months ago now, and the rock falls were just tremendous right along the coast, huh? Just tremendous. And so houses, they lost people then too. It's really sad. Sir.
Have you by any chance been retained to do any analytics in the Marine District in San Francisco?
I would say one word, Berkeley.
Politics.
Okay. I won't elaborate any more than that.
So is there a shear wave velocity threshold that you're trying to achieve in that crust zone?
Yes.
Like-
So what you're saying is, yeah, that's exactly right. So the sad part for me is I wish shear wave velocity going from a real poor soil to a real good soil would be 200% change, and it's about 40% change. So you have to make very precise measurements, and that's really hard selling those things. And you know how many universities teach shear wave velocity measurements and so forth in the United States? Not a whole lot, but mainly because University of Michigan produced some people. We have children. I have academic grandchildren. So that's where they come from. And it's not something that people, it's going to get more and more important for one reason. You know, everything you do, well, many things you do now is based on deformations. Okay, how much is that concrete beam going to deform? It's no longer the strength of the concrete beam, it's how much is it going to deform and so forth. You need shear wave velocity to predict deformations. You don't need strength. Strength, okay, it's nice. I'm on the 9th floor, the 8th floor of the building lecturing, and I look out and I ask the students, okay, is strength controlling any of those things? We won't talk about shrinking, swelling soils right now. Is strength controlling that? No, none of that stuff. You want a factor of safety, but then you also want to make sure that things deform within acceptable limits. And strength doesn't tell you a thing. So we're getting more and more, and the geotechs are probably about as slow as anybody to adopt this. But we're getting more and more. So Professor Gilbert is doing work predicting deformations. I can predict the settlement of footings on sand better than you can with CPT because I can predict it continuously. But you've got to know these sort of things that I'm talking about measuring, and that's much newer, huh? That's a much newer thing. So did I answer the question? Sort
I
of.
think so. I'm just
Okay.
thinking about the engineers in New Zealand, and if they're trying to design an improvement for someone's property, are they trying to achieve a certain shear wave velocity, and that's probably spelled out in their code?
Yeah. I don't know how much it's going to be spelled out in the code. The improvements and so forth should be spelled out in the code. By the way, you should know. So now I've gone down to New Zealand. I've done testing. Maybe they'd like to use me as a consultant and pay me. Oh no, that's a conflict of interest. Shh, stop that. I can't do that. I could get in trouble with the university. I've talked to the head lawyer at the university. I don't want to say why, but I don't have a conflict of interest.
We will not say why.
I've never done anything wrong, but if you're out there so visible, they think you're doing something wrong, huh? And they want to know, okay, what did you do on this and what did you do on that?
Are they taking your work or research and putting that into their building codes?
Yeah.
Or have they already done it?
Yeah, they have already done it. The cross-hole test that you saw there is in the building codes. And I told them they could keep it simple and they could do cross-hole tests. It'd be a little more complex, but I showed them how to do it in mats. You could do that. And so people could easily do that. But surface waves, which is another thing we deal with a lot, surface waves are a much easier way to look at a mat, and the cracks will eat you alive with surface waves, and they might not very much with cross holes. So it just has to do with the way the wave is sampling.
So is most of all the newer residential slabs on a structural or waffle slab system so that they can make adjustments as necessary?
You know, all of these wonderful things that professors talk about, in the code, I have not read the code, so I can't say all the things. But you guys can override us if you will sign for the insurance companies that this is an acceptable way. So there still is that in the codes, but it should really be a waffle structure. And so, as I say, the Japanese are very good. You know, they have that waffle structure now, and they also have a lot of wooden structures and so forth, so it's easier. They ride through earthquakes a lot better, but they re-level easily that way, huh? Yeah. But yeah, it's in the code. I should tell you one other thing. The department chair hasn't heard this. And this is more or less going to be correct. The New Zealand government was very pleased, and within the last year in Washington, D.C., the New Zealand embassy had a party and featured the University of Texas and the work we had done down there, and thanking the National Science Foundation and the University of Texas for things that we had done. Because they were doing this, I mean, I think I got the tail of the elephant. I think, I don't know without testing like that, and it could have been better. That's the problem, but I mean, you continuously learn. But it was a huge help and a real basis for founding and saying some of these things that otherwise it's just going to be a spitting contest, huh? You don't have the basis to make important decisions. So we couldn't be happier.
Any more questions for Ken?
Thank you for staying so long. That was very nice of you.